Okay, folks, take a seat. It's time we have a serious conversation about climate change. Now, this isn't going to be your usual conversation because I'm going to do all the talking. And most of you are not going to really like what I have to suggest, because in the next 50 to 100 years, it's just not going to be sufficient to eliminate the burning of fossil fuels to avoid a crisis. We're going to have to artificially cool the planet. Now, I think most of us have come to realize that climate change is here. It's serious, and we're going to have to do something about it if we're going to continue to inhabit this planet. And I think most of us realize that this is human-caused, and it is principally driven by the burning of fossil fuels. And we get to this point and some people throw up their hands and go about their day because they just can't imagine not being able to drive their cars where they want to or fly to Hawaii in the wintertime. And others go, okay, I get it. Let's quit burning fossil fuels. Sorry, folks, that ship sailed a long time ago, and that's not going to be enough to avoid a crisis. I've been looking at that data and the research studies about climate change. And in the next 50 to 100 years, to combat climate change, we're going to have to artificially cool the planet. My name is Richard Schmidt. I have a PhD in an engineering field called applied mechanics. Now, I'm not a climate scientist, but I am a scientist, and I have done research in a great many fields. And I know about the scientific method, and I know how to think logically and to analyze data and various hypotheses. But more importantly, I have granddaughters that are going to depend on us to navigate through this crisis. Now, let's take a look at some of that data. When it comes to climate science, the most important data has to do with the accumulation of greenhouse gases in the atmosphere. And where we get the best information is from ice cores. These are cores of ice taken from the Antarctic, Greenland, a number of other places. And in the Antarctic, as snow is accumulated over the years, it compacts and forms ice. And when it forms that ice, it traps the gases and other information that is the conditions of the Earth at the time it was deposited. So as they core down into the Antarctica, they are able to pull out cores as old as 800,000 years. And during each level, it's like little time capsules as they come up to the surface. Older being deeper, more shallow being more like current time. They're able to get a lot of information. In particular, the most important information is the levels of CO2, carbon dioxide, and the temperature at that time. That's accumulated into the following graph. Now you see on the x-axis here, we start from present time and we go back in time 800,000 years. On the left axis is the blue axis here is the level of carbon dioxide at that time. So the blue data is the rise and fall of carbon dioxide over the last 800,000 years. On the right axis, the red axis, is temperature in degrees centigrade. And you see the temperature of the Antarctic at that time. Now, when this data first came out, there was some debate as to whether or not the CO2 levels rising caused the rise in temperatures or the other way around. You notice how they definitely rise and fall together, so they're clearly linked. These two parameters are in lockstep with each other. The other thought was, well, maybe it's the rise of temperature that causes the rise in CO2. Maybe rising temperatures release more carbon dioxide. That's what a lot of the fossil fuel industry hoped that data would say, but in subsequent studies, it was pretty well proven that in fact it is the rise of CO2 that causes the rise in temperature. Now you see for 800,000 years, CO2 rising and falling. And it never goes above 300 parts per million on this axis here. 300 parts per million until you hit here. This is essentially present day. This is 200 years ago, roughly, the Industrial Revolution. That's when we started to burn fossil fuels, oil, coal, natural gas, and we're releasing CO2 into the atmosphere. We'll come back to this in a minute, but you notice how it did rise above 400 parts per million, and that's where it is today, and it is still rising. We'll come back to this information when we talk about what happens if we can begin to eliminate the burning of fossil fuels. Does this chart immediately come down, and does it come down fast enough to save us from an increase in temperature that would be perilous to life on this earth? In the meantime, let's look at some other information. What is the temperature of the Earth? On average, the Earth's surface temperature is 57 degrees Fahrenheit. Now, by average, I mean the Arctic, the Antarctic, the equator, winter, summer, average it all out, the Earth's temperature is roughly 57 degrees Fahrenheit. What's the temperature on our nearest neighbor? Nearest neighbor is Venus. Venus, by the way, is clouded with CO2. Its atmosphere is almost entirely carbon dioxide, and its temperature is 847 degrees Fahrenheit. Now you might say, well, yeah, but Venus is a lot closer to the sun than the Earth. Yeah, it is, but Mercury is a lot closer to the sun, and it's only 354 degrees. The difference is the greenhouse gas called carbon dioxide. Now, when we talk carbon dioxide, how much of the air do you think is carbon dioxide? We put a lot of emphasis on it, but it's really a very small component of our atmosphere. Our atmosphere is primarily nitrogen at 78%, oxygen at about 21%. The next most prevalent gas is argon at almost 1%. Carbon dioxide is only 0.03%. And it's kind of interesting because when this chart was made, carbon dioxide was 0.03%, but now it's 0.04%. So we need to modify this graph. So now let's look at some of the consequences of climate change. Most of this we're very familiar with. We've seen it before. The first on the list is sea level rise. We've heard that, as we warm the planet, the Antarctic, Greenland begin to melt and the sea level will rise. I saw in just today's paper, for example, that the West Antarctic ice sheet is expected to melt no matter what we do at this stage. And it will take a long time for that to take place, but it will result in a rise of about 6 feet. Saw another article just a few weeks ago about the Greenland ice sheet. It was actually trying to put a positive spin on things. It said as long as we can keep the temperature rise to 2 degrees centigrade, we should be okay. Keep in mind, we're already at 1.2 degrees temperature rise from the pre-industrial average. So we don't have a lot further to go. But if we do exceed 2 degrees centigrade, and keep that number in mind, we'll be back to that the Greenland ice sheet would collapse. And that would result in a sea level rise of 23 feet. That bodes ill for coastal cities like Miami, New Orleans, Venice. Okay, weather changes. We know we've got a lot more storms these days, droughts and floods, heat waves. And by the way, heat waves actually kill more humans than all these others combined. Wildfires. We're seeing a lot more wildfires. There were huge wildfires in Canada this summer. And this is a kind of a two-edged sword because when you lose the trees, not only do you emit carbon dioxide from the burning of the trees, but you lose the trees itself. You lose the tree's ability to take in carbon dioxide and expel oxygen. We need more trees. So this is a bit of a tipping point. Ocean acidification, obviously, as the CO2 rises, the ocean absorbs a lot of CO2, but it acidifies the ocean in the process. All of this results in a reduced food supply, and we need to continue to be able to feed 8 billion people on this planet, as well as animal extinctions, obviously. One thing you may not have heard about or thought about is that as temperature rises, there's another tipping point, the thawing of permafrost. As permafrost thaws, methane is expelled. And methane is a much worse greenhouse gas than carbon dioxide. It is, in fact, about 90 times worse in terms of trapping heat from as a greenhouse gas. Okay, so since it was the burning of fossil fuels that got us into this mess, can we get out of it by simply eliminating or at least reducing the burning of fossil fuels? Seems like an obvious question. Before I answer that question, let's get a little progress report. How are we doing so far? We've all seen a lot more electric cars on the roads. That's a good thing. We see solar collectors everywhere, fields of solar collectors generating electricity, solar collectors on rooftops, heating water and generating electricity. We're seeing a lot more wind farms, wind turbines generating electricity. All these green things are all very good. So you would think maybe we're reducing our dependence on fossil fuels. Guess what? Not so much. World consumption of fossil fuels is continuing to rise. Now you see a little blip in the chart here. That was the pandemic. Industries closed, people stayed in their homes. We actually, for a short period of time, reduced our consumption of fossil fuels, but that little blip is over and we are now back to where we were before, and it is still rising. So as they like to say, how's that working for you? Not so good. But let's go back to the premise. What happens if we can manage to drive this down, even to zero? It takes us back to our original chart, this graph of the ice core data. Now, the first thing to keep in mind is that the carbon dioxide life cycle is about 200 years on average. That is, a carbon dioxide molecule will stay in the atmosphere approximately that long. So this is a slow process. And if you remember from this previous chart, here was industrial age. We were sitting a little below 300 parts per million and went off the charts above 400 parts per million, and it's still rising. So what happens to this level of CO2 if we should be able to eliminate fossil fuels? Harvard did a study recently. It said if we were to eliminate all fossil fuel burning tomorrow, they found that it would take 50 years before the CO2 level would come down. It would continue to rise for an additional 50 years. So that's not an immediate fix. We need to do that. We need to reduce our dependence on fossil fuels, but it is not an immediate turnaround of CO2. Okay, so what happens to this temperature if the CO2 doesn't come down? If you look back in history on this chart, and you look very carefully, you find that the CO2 level rose and then temperature followed suit, but it took about 100 to 200 years for that to happen. So there was a delay, a lag in the system. But keep in mind, it's already been about 200 years since we started the Industrial Revolution, and temperatures are beginning to rise. Now, there are a lot of sophisticated models that try to predict how fast the temperature will rise depending on the levels of CO2. And I'm not about to go into all those models. But let's just take a look at this chart and imagine for yourself, what do you think happens? Look at this red line. How far do you think it's going to go up? 5 degrees? Doesn't seem like an extreme prediction to me. 5 degrees centigrade is cataclysmic. We can't possibly sustain a 5-degree rise in temperature. Let's go back and take a look at the Paris Climate Accord. Paris Climate Accord said we'd really like to prevent the temperature from rising from pre-industrial levels to no more than 1.5 degrees centigrade. Mind you, we're already at 1.2. Why do they say 1.5? Because they see above that bad things happening. But we just looked at that other chart and we said 5 degrees doesn't even look to be out of the realm of possibility. 5 degrees is cataclysmic. I don't think we're going to make 1.5. I don't think we're going to make that 2 degrees rise that prevents the Greenland ice sheet from collapsing. Okay, I know this is all gloom and doom, folks, but there is a silver lining. I think there is a temporary way out of this. I think there are ways that we can artificially cool the planet temporarily to get us to the point where we can eliminate the use of fossil fuels. There's a woman at a company called Silver Linings called Kelly Warner. She calls this emergency medicine for the planet. Now, the general terms for artificially cooling the planet, called solar geoengineering, you may begin to see this term, or solar radiation management are the two kind of buzzwords, SRM for short. Now, no matter which method we use, and I'll mention a few of them, no matter what we try, they must be reversible. We must be able to change course. If we put one of these in place and something doesn't go the way we expect, then you should be able to shut it down immediately. Now, I will tell you that there is a league of concerned scientists going around the world trying to get countries to sign a ban on any such solar geoengineering, any such idea of artificially cooling the planet. They even want to get countries to ban research on the subject. Their arguments, they say, well, we don't want to mess with Mother Nature. Really? What do you think we've been doing for 200 years? This has been a crazy experiment. Let's put a bunch of CO2 in the air and see what happens. We've been messing with Mother Nature for quite some time, so that argument doesn't hold water for me. They also say, well, it would take our emphasis off getting off fossil fuels. This would be like a get out of jail free card. Yeah, I get that. And yes, we do need to eliminate the use of fossil fuels. That's just a little naive. We've got to survive to the point where we can make that happen. The third argument is a really good one. They said, well, we need to know what the side effects of any of these things would be. But guess what? If you ban research, you're never going to know what those side effects are. So my plea is to allow the research on these subjects to begin now, so we can put something in place when it becomes absolutely necessary, and I believe it will become absolutely necessary. Let's take a look at some of the concepts. One thing that scientists noticed back a few years ago, Mount Pinatubo erupted in 1991. This was the largest volcanic eruption in the 20th century. It put a lot of ash, aerosols, sulfur dioxide in the stratosphere, and it cooled the planet. It actually cooled the planet by about 0.5 degrees centigrade, which is a lot, and it did so for 4 years. So people immediately started looking at, is there a way to imitate a volcanic eruption? Sure, several concepts. Here's one of them. in this embodiment, you have a ship moored someplace and a long tube or tether going up to a balloon. This tube allows you to inject or pressurize some aerosol, maybe sulfur dioxide. Now, there's been some people that looking at sulfur dioxide, they say, well, looks like there'd be a bad side effect of ocean acidification. They're looking at calcium carbonate as a possibility. In any case, that's why we need to do this research. If this particular concept, which is kind of cool, a ship pumping aerosols up to a balloon, and it would be in various locations around the world. If this didn't pan out, you could do it with airplanes. Put the sulfur dioxide or whatever you're going to put in the stratosphere into an airplane, fly it up to 60,000 feet and release it. I don't like that concept as much because it requires the burning of fossil fuels to make it happen. But it's at least very feasible and can be done anytime. But we need to conduct the research to understand the side effects. There's two very good things about this particular concept. One is the results are immediate. Once you put the sulfur dioxide or other aerosol in the stratosphere, you cool the planet immediately. The other thing is, it's cheap. Harvard made an estimate of what it would cost to cool the planet by a sufficient amount to make life reasonable. And the number they came up with, rather than giving it to you in billions, I'll just say, let's say, and of course you want the world to pay for this, right? But let's just say, for sake of argument, that us Americans are going to step up and we're going to foot the bill entirely by ourselves. What would it cost the average American? $7 a year. $7. It's cheap. All right. So it's at least worth conducting the research. And I mentioned that because actually a couple of years ago, there was a small research experiment that was going to be conducted with a balloon in Sweden, just to test a small quantity to see if this thing is feasible. Protests shut it down. Was not allowed to proceed. It's in the process of being rescheduled and will happen someplace else on the earth. But that's what we're dealing with. We're dealing with a resistance to this that is unreasonable in my view. There are some other concepts as well. Well, some people think you can just foam the ocean, create a bunch of foam bubbles around the ocean and reflect sunlight back and reflect it back to the sun. Reasonable? I don't know how effective this could be. It's being looked at. Another one is actually brightening marine clouds by pumping salt water up into the atmosphere. There is actually research being conducted as we speak in California on this concept. It seems very benign, simply pumping salt water up and high into the atmosphere and brightening the clouds to reflect more sunlight. A simple plan, which seems almost too simple, is to actually paint buildings and other surfaces white to reflect sunlight. We have a lot of surfaces on the earth that are dark and black that absorb sun. Painting buildings and other surfaces white or a lighter color, this is called the albedo effect and can have actually a significant effect. Now, if you want to go high-tech and kind of spacey, MIT came up with a concept. Space bubbles. This is for real. They're saying, well, we just have these rocket ships go up in space and they assemble this big umbrella of silicon space bubbles. Where do they do it? Well, they do it at a place far from the Earth. It's at a point they call the Lagrangian point. And this is a point where the gravitational pull of the Earth and the sun are in balance. So it has no tendency to drift one way or the other. This space bubble has got to be about the size of Brazil for it to work. They claim it's feasible. I don't know. Maybe we should conduct some research on that one. All of this is to say, We need to conduct research on these and other possible concepts now so they be in place by the time we need to make the decision on what to do. I also would direct you to a couple of wonderful TED Talks. One talk by Kelly Warner, A Silver Lining, and another by Dr. David Keith of Harvard. These are very knowledgeable climate scientists. They know a lot more about this subject than I do. And I direct you to their TED Talks to educate yourself more. I want to leave you with a joke. This is a little cartoon from Rubes. We've got Frank here writing in his journal. This is his final journal entry. Water started out tepid, now seems comfortably warm. Starting to feel as if the boiling frog theory is nothing but an urban myth. Actually, it is an urban myth. The frog in water that gets warm will jump out, but it is a nice metaphor for the situation we're in. I want to thank you for your time today and your patience. I know I did all the talking, but we needed to have this serious conversation about climate change. Take care.